So for a body of work titled Artificial Intelligence for Safety Critical Surveillance Systems at Confirmation Review, the agenda is as follows, and it's the problem space, and then the position, the state of the art, the method, the initial results, the future work, and some plans and Gantt charts. So the problem space is in AI to EW in platform protection, and this has interests in the military, but our particular interest is in civil applications. Our approach is neurosymbolic AI, which is a division between symbolic AI and neuron approaches, but we also have interests as well within accessible data sets, which is a problem in the civil domain. So the current approach has been divided into the neurosymbolic AI approach and also into the dataset creation and refinement approach. And the first initial work was to look at an expert system. Expert system was selected because of its higher level of abstraction to human knowledge at a human level. And the first initial work that we looked at in there was looking at a neuron approach to try and do rule extraction in order to create rules for the expert system as a neurosymbolic AI approach. This caused us to be able to have to to deal with repeatable determinism and mission criticality in neuron approaches. So we want to further that work with a bit of machine learning into the neuron approach with the random forest algorithm in the expert system to apply the random forest to the guard equations of rules. As well as that, what we need to do is actually gain some data sets in order to operate with the research, and as part of that work we did a synthetic dataset generator with a markup language controlling that, and that is going to build on to a GAN approach. So the idea beyond that is maybe to look at transferred learning to deal with the element of surprise in the application area. So in that research area, what we can see is that the green areas have already been touched. The orange areas are the areas that are high priority, and the silver areas are later down the plan. So in the state of the art, the area of particular interest is the neurosymbolic AI approaches, and there's been some interest in that area. We've been interested also in the expert system approach because of its ability to use rules that are humanly understandable. And Malin and Spiegel et al. Had approaches for this, but their approaches were grading rules rather than generating new rules. Our approach is to generate new rules using a rule extraction approach. So as part of that, also we're interested in the random forest work by Leonard and Jared Bayou. And as part of that work, we also had to touch on repeatable determinism to make neuron approaches repeatable and therefore closer to safety critical for the application area. And as part of that work, we've also been interested in rule extraction, and we did some early work on that work, and there's some survey papers and also some early work towards a convolutional approach, which is not actually rule extraction, it's more like success criteria. So that area is still active. In the GAN approach, there's been a lot of activity. Goodfellow's approach originally, perhaps supported and influenced by Schmidt-Huber. But the areas here of interest is high resolution multi-mode prediction, i.e. multiple answers, the mixture GAN approach, and latent space. So in our method, we used a decompositional approach, basically by asking questions and breaking down into research areas, and the green areas is what we've been currently working on. So with that approach, we've been embracing the neurosymbolic AI approach, and we have been dividing our work, therefore, into neuron approaches into repeatable determinism and formula extraction, and into symbolic AI with an algebraic expert system for dealing with missing data, etc., and machine learning. And for dataset creation, we've been looking at a dataset creation prototype, which we have, and started looking towards GAN's approach and transferred learning in the future later on in the plan. So the initial results, the findings with repeatable determinism, what we were able to do was grow the weights in different ways using non-random schemes, and you can see there between the original form and non-random form that we have a weight matrix there which has alignment and correlation with pixel positions and the number of loads, so it's actually growing them in a way that might be more useful to rule extraction because things are adjacently located. Also, we looked at some of the problems with CPUs, because that's exclusively mostly what I've been using given my remote location, and there were some issues there from a sort of computer science point of view which helped to increase the accuracy. We took that work on further into convolutional layers, and the convolutional layers we were able to create a convolutional form of non-random initialization states which would actually provide higher accuracy and also induces earlier learning, so there's less unlearning of the initial state. This was done by a number system which is more striped rather than speckled as the random form is, and that has advantages for better accuracy and earlier learning. In the expert system approach, we took the expert system approach and kind of made it a little bit more neural network-like. It's an algebraic form. It also allows facts to have a number of values, and those can virtualize nodes, and then they're organized into input, hidden, and output layers. And then the output layer is using a modified histogram technique in order to perfect the values based on all those. The advantage of this is that the individual nodes have an individual permutation of and probability with them, rather than in a neural network approach where the individual probabilities would be distributed over many nodes and overlapped with others. As part of some of the sort of early work towards rule extraction, we had a sort of formula extraction method where we were using a particular input representation which will allow us to extract relationships between inputs and outputs in layers. This was done in perceptron layers, and what it was able to do with that is we could put in a magic formula and train a network, and we could deduce the mathematical operator relationships from the inputs to the outputs. Also with that work, what we were able to do was reverse those deduced relationships and find a function which deliberately hadn't been put in the inputs but was part of the layer. You can see that in the bottom right, which is a sine function. As part of the synthetic dataset creation, we created the markup language in order to be able to model radar systems, and to be able to then subject those to image classification in order to test that data generation to see if it was conducive to AI approaches, and we had some competitive results there. So there was a certain complexity to that work, and the important point here is that there are parameters here, dynamic and semi-dynamics, and these dynamic and semi-dynamic parameters can be set live, and they will be useful towards a future GAN approach as a generative model of a GAN approach. So considering the work that's already been done, then what we need to do is consider the work that we wish to do. We can see the orange and silver areas, and we can generate those into priorities of bronze, silver, gold in order to be able to schedule those into a Gantt chart, and we can see that the initial work is around about the neurosymbolic AI, and the silver work, which is further down the plan, is more about GANs and data sets and transferred learning. And then of course there's a necessary action, which is to write up the thesis and critically appraise everything. So the actual plan looks a little bit like this, and it starts in 2020 and runs to first quarter of 2022 for the bronze, silver towards 2023, and then 2024 is actually where we hopefully are ready to complete. However, the contract does actually run to 2026, so we do have a bit of slip in the plan. I hope that was of interest.